Have you ever considered why some electrical devices, despite consuming power, do not perform any visible work, or why electrical grids need more than just the energy that lights up your home? It is a fascinating aspect of alternating current circuits, distinct from the power that runs your appliances. Reactive power is the portion of alternating current power that oscillates between the source and the load, continuously building and collapsing magnetic or electric fields. Its primary function is to provide the necessary excitation for inductive loads, such as motors and transformers, and to charge capacitive loads, like long transmission lines or capacitor banks. However, unlike real power, reactive power does not perform any useful work or produce heat. Instead, it is stored and then returned to the source within each alternating current cycle. The fundamental reason reactive power exists stems from the nature of alternating current and the components that interact with it. In alternating current circuits, voltage and current continuously change direction. Inductors store energy in a magnetic field when current flows through them, and capacitors store energy in an electric field when voltage is applied. This energy is not consumed. It is simply borrowed and then returned to the system. When current and voltage are not perfectly in phase, meaning they do not peak and trough at the same time, this phase difference gives rise to reactive power. The power factor, a crucial measure, quantifies how effectively real power is being utilized, with a lower power factor indicating a greater presence of reactive power. Understanding reactive power is crucial for electrical system operation and design. Excessive reactive power flowing through a system can lead to several practical issues, including increased current in conductors, which in turn causes higher ohmic, or I2R, losses. This means more energy is wasted as heat, reducing overall system efficiency and requiring larger, more expensive wires and transformers. It also contributes to voltage drops across transmission lines, which can negatively impact the performance of connected equipment. To mitigate these effects, engineers employ techniques like power factor correction, often using capacitor banks, to supply or absorb reactive power locally, thereby reducing the reactive power demand on the utility grid. This intricate balance between real and reactive power forms what is known as apparent power, typically measured in kilovolt-amperes, or kVA, while real power does the actual work, measured in kilowatts, or kW, reactive power, measured in kilovolt-ampere reactive, or kVAR, is indispensable for maintaining voltage levels and stable operation across the electrical grid. Utilities often monitor and manage reactive power carefully, sometimes imposing penalties for poor power factor because it strains their generation and transmission infrastructure without contributing to useful energy delivery. Synchronized generators are key players in this, as they can be precisely controlled to supply or absorb reactive power to support grid voltage. Ultimately, reactive power, while not directly performing work, is an indispensable component of alternating current electrical systems, facilitating the operation of essential equipment by establishing and maintaining electromagnetic and electrostatic fields. Its effective management is fundamental to ensuring the efficiency, stability, and reliability of power distribution, leading to more robust and economical electrical networks for everyone.